Hello and welcome to video 32, where we're going to look at a flying pig, if you can believe that. Those of you who were in class probably saw it. Those of you who weren't can actually see it on YouTube. It's video 31. And when you play this, you can see that the pig goes around in what's known as conical pendulum. So it goes around with some frequency and it makes some angle from the vertical, as you can see in the picture here. And that angle and that frequency depends on the speed of the pig. Our pig here has a constant velocity that's really determined by the forward force provided by the wings and the drag force. Sort of like when you hit the gas pedal in your car, there's some terminal velocity like speed that you're going to maintain a constant speed. Same thing here, so it's going to go in a circle. And we want to analyze this motion, and we want to calculate a theoretical period based on this angle. So to help us do that, I am telling you that this is 90 degrees. So the string is 90 degrees, not 90 degrees, 90 centimeters long. And I've provided, to make it somewhat interactive, lines here so that we can read off the height from the ceiling. And based on this, I'm going to go ahead and call that 60 centimeters. So let's see what that means in terms of our calculations. This distance here is going to be 60 centimeters. So that's this distance here. And this length you're given is 90 centimeters. And that's going to allow us to calculate the angle. So to calculate that angle, you can see that this is the adjacent side relative to that angle, that theta. And this is the hypotenuse. So the cosine of the angle we're interested in is equal to the adjacent side, 60 centimeters, divided by the hypotenuse, 90 centimeters. So when you take the arc cosine or inverse cosine of that, you get an angle that is 48.2 degrees. Now, as long as I have the picture up here on the screen, I'd like to point out that when we look at centripetal motion here, we're going to need to know the radius of the circle. And we can express that in terms of this length and this angle. So as you can see, this is the opposite side of the theta. This is the hypotenuse again. So that R is going to be equal to L sine of theta. And that will be useful to us in a minute or two. So let's go ahead and start answering some of these questions. Calculate the theoretical pendulum. Well, that's really a big question. That's the crux of the whole problem. If we were to draw a free body diagram of the forces acting on our piglet friend here, you would find out that there's a weight force. Makes sense. He was a good-sized pig. There's also going to be a tension force going along the same direction as the L. Now, we need to conceptually understand that this tension force has two components. There's a component that's directed towards the center of the circle, and there's a component that's directed upwards. So this is the Y component, if you will, and this I'll call centripetal. If this angle's theta, that would make this angle theta. So that's going to mean that the Y component is going, and this is T, that's going to mean the Y component is going to be T, the magnitude of the tension, times the cosine of the angle, because it's the adjacent side. The centripetal force here is the opposite side of this triangle relative to the theta. So that's going to be T times the sine of theta. And as we just saw on the other page, this distance R is going to be equal to L sine of theta. All this is going to be really useful. I feel like I'm talking to my daughter and Thomas the Train being a useful engine, but it's going to be useful. We want to look at the forces in both the Y direction and the X direction. In the Y direction, there's two forces acting. There's the Y component of this tension, and then there's the weight force down. And we know that those have to be equal. So the Y component has to be equal to the weight force. And the reason I know that is that if they were not equal, the pig would accelerate downward or upwards, and he doesn't. He just goes into a circle. Sorry if I'm being presumptuous about him being a he. But the Y component, as we said, is going to be T times the cosine of theta. Remember, you always want to look at the diagram. Sometimes when you see y component, you think, oh, sine of theta. And it is if that's the reference angle, but here you need to look at the actual diagram. So let's go ahead and solve this for t. That'll be useful later. And the tension is going to be equal to mg over the cosine of theta. And that kind of makes sense. The faster you spin this, the greater this theta is going to be, the smaller the cosine theta is going to be, and the bigger the tension is going to be. But let's look in the x direction now. The x direction is the one that's got a lot going on. First of all, there's a centripetal force towards the center of the circle, and if we apply Newton's second law, F equals ma, centripetal acceleration. So F net equals ma, F centripetal equals ma centripetal. Now, centripetal isn't actually a force, it's just a direction. You have to look at the problem to see what's actually causing the force. In this case, the cause is that tension force here that is pulling it towards the center. And we've already found that that tension here is going to be equal to this. Well, that tension is going to be the x component of the tension, which we'll get to in just a second. And it's going to be mass times centripetal acceleration. Now, centripetal acceleration, you've seen it in multiple ways. On the one hand, it's tangential velocity squared divided by the radius. And on the other hand, remember relating angular quantities to linear quantities, the tangential velocity is equal to omega r, or the centripetal acceleration is equal to omega squared r when you plug that in there. So it's going to be equal to omega squared r. And that's what I'd like to go with. Now, I understand this is a lot of moving parts. We can actually get rid of the omega. Omega is angular velocity, which is a little different than frequency. Angular velocity is the number of radians per second. It's a way of quantifying how quickly this is rotating, regardless of what radial position you are on there. So every single rotation represents 2 pi. Now, one rotation per second is known as the frequency. So omega, or little w, is 2 pi f. Sometimes, like in this case, we're looking for the period. It's useful to express this in terms of the period rather than the frequency. And recall that they're inverses of one another. So period represents 1 over the frequency. So if I rewrite this as 2 pi over period, that's going to be the omega. So what does this all mean? Let me go back to the blue, and I will write AC first as omega squared r. Let me get back to the thick blue. And there's a couple things to plug in here. So if I take the Tx, I can replace that as the magnitude of the tension times the, again, looking at the figure, not just memorizing sines and cosines. According to the figure, it's the opposite side, so it's going to be T sine of theta equals m. Now, our omega, in terms of period, by the way, let's not use T for period. Let's go ahead and use P. I know normally P is used for momentum, but here I want you to think about it as period. I just don't want people to confuse the T from period with the T from tension. So let's write it this way. When I plug this, I use here, in for omega, I'm going to get 2 squared, which is 4, pi squared, which is pi squared, over the period squared. We're not done yet. We also have this r. Remember, this r is the radius here. I probably should have made this lowercase r. We want to express that in terms of L, theta, things we already know. And we've already done that. Remember, r equals L sine of theta. I'm going to go ahead and write L sine of theta in its place. One more step we want to do is we actually want to replace the t. So from the y direction, we can see that the magnitude of the tension is equal to this stuff, mg over cosine theta. So as I jokingly say in class, we're going to make this t disappear, not in the mafia way. And we plug that in and rewrite all this again. So this is going to be mg over cosine theta, because that's the same thing as tension, times the sine of theta equals m times 4 pi squared L sine theta over period squared. I know that's a mouthful, but there's a reward. The masses, they cancel out. Our period is not going to depend on the mass of the pig. It's also got sine theta on both sides, so we can cross that off. And let's just do just a little bit of algebra here. I'll bring the p squared over here, because remember p, or period, is what I'm solving for. P squared g equals 4 pi squared L. This is over cosine theta, so I'm going to multiply that and get this cosine theta. P squared is going to equal 4 pi squared L over g cosine theta. And I'm going to take the square root. Now, I like to take 4 pi squared and turn that into 2 pi outside of the radical. Anytime you have something that is repeating like this, anything that is a uniform circular motion kind of activity, I like to write it in terms of 2 pi. So if you'll allow me, I'll take the square root of this and then the square root of that. So the square root of 4 pi squared is 2 pi, and the square root of L over g cosine theta is the square root of L over g cosine of theta. So we've got now a theoretical expression for the period of the pendulum. Cool. How many of you have lost track of what the point of the whole problem was? Let's see what the actual numbers are when we plug it into here. So what's our theoretical period going to be? So if I take these numbers and I start plugging them in, let me just give us a little room to work here. Period, I like the thicker marker. Period is going to be equal to 2 pi times the square root of the length, which you're told is 0.9 meters, times the cosine of the angle, which we got 48.2 degrees. Remember, we took 60 degrees for the height, and then we took the 60 centimeters rather, and 90 centimeters for the hypotenuse, the length of the wire, and we got 48.2 degrees. And we're going to divide that by 9.8, the acceleration due to gravity on Earth. So if we had this flying pig on a different planet, it would have a different period. But it's on Earth, so we can all make the same calculation. And when I plug in the numbers for that, the number I get is 1.55 seconds. So the theoretical period of the flying pig is just over 1.5 seconds. Let's compare that with the period we get from watching the video. So let's go ahead and let's watch the video. And what we're going to do is we're going to time it. So if I time it starting now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I get a time. The time I got when I did that was 16.3 seconds. You may get something slightly different, but I'm getting 16.3 seconds. So when we do this experimentally, get a different, thicker marker anyway. I got 10 revolutions, and it took me 16.3 seconds. So when I get the period, that's going to be equal to the total time, 16.3 seconds, divided by the number of revolutions, 10 revolutions, gives us 1.63 seconds for the experimental period. Theoretically, you've got 1.55, so this is theoretical. And those are pretty close. Let's go ahead and quantify that and do percent difference. So for percent difference, I'm going to take the experimental 1.63 seconds minus the theoretical 1.55 seconds divided by 1.55 seconds, the theoretical. And for you purists out there who like to multiply by 100, you're going to get a percent that is about 5%. So that's pretty cool that we can get this to within 5%. At least I think it's cool. Now we have a few more things I'd just like to calculate, and those would be relating the angular quantities to the tangential quantities and looking at the centripetal acceleration of the pig. So if we want to calculate the angular velocity, in other words, the angular velocity, that is going to be 2 pi, remember 2 pi for every revolution, times the frequency, which is the number of revolutions per second. So number of revolutions per second times the number of radians per revolution will give you the radians per second, which is what we want. Since we already have period, let's go ahead and solve that in terms of 2 pi over t. So I plug in the numbers. It's 2 pi divided by the time. Let's go with the theoretical 1.55 seconds. Gives me an angular velocity of 4.05 radians per second. Don't confuse that with plain old frequency, which is revolutions per second. So we've got the angular velocity. Let's get the tangential velocity. These really shouldn't be A, B, C, D, but that's okay. The tangential velocity is going to be, when you relate the tangential to the angular, it's going to be omega r. Now, just to point out here, if you go a whole circle, 2 pi r over t, and it's constant velocity, you can take the circumference divided by the period. That will work if it's a constant angular velocity. But let's go ahead and do it the more general way of angular velocity at a moment in time times the radius. So the angular velocity, which granted is the same the whole time, of 4.05 radians per second, times the radius, which is, and this is important to point out, the radius is not 90 centimeters. Recall that r equals L sine of theta, so it's going to be 0.9 meters times the sine of 48.2 degrees. Gives me a radius, I think I used little r, radius of 0.670 meters. So when I plug that in here, 2 pi times 0.670 meters divided by the period. I know I switched over to the t, but the period is 1.55 seconds. When I plug that in, I am getting a tangential velocity of 2.72 meters per second, which is pretty close to, sorry about that. Again, sorry about that. But I think I was saying that this is about 6 miles an hour for those of you interested in being flying pigs. The centripetal acceleration we can calculate one of two ways. You can either take the tangential velocity squared divided by the radius, or you can use the angular velocity squared times the radius. In either case, you're going to get the same answer. So when you take the tangential velocity of 2.72 meters per second, square it, and divide by the radius, 0.670 meters, or if you take the angular velocity of 4.05 radians per second, squared times the radius is 0.670 meters. Either one should give you centripetal acceleration that is about 11 meters per second squared. Finally, if we want to get the centripetal force, you're basically applying Newton's second law. F net equals ma. The centripetal force is equal to the mass times the centripetal acceleration. On the board, if you looked, you could see that the mass of the pig was 160 grams. Don't forget to convert to kilograms. And the centripetal acceleration we just calculated is about 11 meters per second squared, which is going to give us a centripetal force that is about 1.76 newtons. So I know that was a lot of work, a lot of calculations. This covers most of what you need to know about rotational kinematics. It's a good application of Newton's second law in 2 dimensions. There's definitely a lot of things going on there, but you also don't see a pig fly every day. And now that you have these skills, if there's ever a job opening for a flying pig farm, maybe you could take them up on their offer. I know this is a long video, but YouTube gives me more time. If you're still listening, I commend you on your endurance, and I hope that this helps you.